We tend to be told in algebra class that if we have a line, our line will have a constant rate of change of y with respect to x. Or another way of thinking about it, that a line will have a constant inclination, or that our line will have a constant slope. And our slope is literally defined as your change in y. This triangle is the Greek letter delta. It's a shorthand for change in. It means change in y. Delta y means change in y over change in x. And if you're dealing with a line, this right over here is constant. Constant for a line. What I want to do in this video is to actually prove that using similar triangles from geometry. So let's think about two sets of 2 points. So let's say that's a point there. Let me do it in a different color. Let me start at this point and let me end up at that point. So what is our change in x between these 2 points? So this point's x value is right over here. This point's x value is right over here. So our change in x is going to be that right over there. And what's our change in y? Well, this point's y value is right over here. This point's y value is right over here. So this height, or this height, is our change in y. So that is our change in y. Now, let's look at 2 other points. Let's say I have this point and this point right over here. And let's do the same exercise. What's the change in x? Well, let's see. If we're going this point's x value is here, this point's x value is here. So if we start here and we go this far, this would be the change in x between this point and this point. And this is going to be the change. Let me do that in the same green color. So this is going to be the change in x between those 2 points. And our change in y, well, this y value is here. This y value is up here. So our change in y is going to be that right over here. So what I need to show, I'm just picking 2 arbitrary points. I need to show that the ratio of this change in y to this change of x is going to be the same as the ratio of this change in y to this change of x. Or the ratio of this purple side to this green side is going to be the same as the ratio of this purple side to this green side. Remember, I'm just picking 2 sets of arbitrary points here. And the way that I will show it is through similarity. If I can show that this triangle is similar to this triangle, then we are all set up. And just as a reminder of what similarity is, 2 triangles are similar, and there's multiple ways of thinking about it. So you're similar if and if only if all corresponding, or I should say all 3 angles are the same or are congruent. So all 3, and let me be careful here, they don't have to be the same exact angle. The corresponding angles have to be the same. So corresponding, I always misspell it. Corresponding angles are going to be equal, or we could say they are congruent. So for example, if I have this triangle right over here, and this is 30, this is 60, and this is 90, and then I have this triangle right over here. I'll try to draw it. So I have this triangle where this is 30 degrees, this is 60 degrees, and this is 90 degrees. Even though their side lengths are different, these are going to be similar triangles. They're essentially scaled up versions of each other. All the corresponding angles, 60 corresponds to this 60, 30 corresponds to this 30, and 90 corresponds to this one. So these 2 triangles are similar. And what's neat about similar triangles, if you can establish that 2 triangles are similar, then the ratio between corresponding sides is going to be the same. So if these 2 are similar, then the ratio of this side to this side is going to be the same as the ratio of this, let me do that pink color, of this side to this side. And so you can see why that will be useful in proving that the slope is constant here. Because all we have to do is, look, if these 2 triangles are similar, then the ratio between corresponding sides is always going to be the same. We've picked 2 arbitrary sets of points. Then this would be true really for any 2 arbitrary sets of points across the line. It would be true for the entire line. So let's try to prove similarity. So the first thing we know is that both of these are right triangles. These green lines are perfectly horizontal. These purple lines are perfectly vertical because the green lines literally go along the x or go in the horizontal direction. The purple lines go in the vertical direction. So let me make sure that we mark that. So we know that these are both right angles. So we have one corresponding angle that is congruent. Now we have to show that the other ones are. And we can show that the other ones are using our knowledge of parallel lines and transversals. Let's look at these two green lines. So, and I'll continue them. These are line segments, but if we view them as lines and we just continue them on and on and on, so let me do that just like here. So this line is clearly parallel to that one. They essentially are perfectly horizontal. And now you can view our orange line as a transversal. And if you view it as a transversal, then you know that this angle corresponds to this angle, and we know from transversals of parallel lines that corresponding angles are congruent. So this angle is going to be congruent to that angle right over there. Now we make a very similar argument for this angle, but now we use the two vertical lines. We know that this segment, we could continue it as a line. So we could continue it if we wanted as a line. So just like that, a vertical line. And we could continue this one as a vertical line. We know that these are both vertical. They're just measuring, they're exactly in the y direction, in the vertical direction. So this line is parallel to this line right over here. Once again, our orange line is a transversal of it, and this angle corresponds to this angle right over here. And there we have it. They're congruent. Corresponding angles of transversal of two parallel lines are congruent. We learned that in geometry class. And there you have it. All of the corresponding, this angle is congruent to this angle is congruent to that angle, and then both of these are 90 degrees. So both of these are similar triangles. So both of these are similar. So let me write that down. So we know that these are both similar triangles. And now we can use the common ratio of both sides. So for example, if we called this side length A, and we said that this side has length B, and we said this side has length C, and this side